right. Yesterday's presentation was brought to you by the Ivan and Steve show. We're going to mix things up, and today it's going to be the Steve and Ivan show. So, just to keep things real here. So I'm going to talk about achieving robust, reliable systems with 10 gigabit or 10 gigabaud signaling and beyond in OpenVPX. And Ivan's going to be talking about thermal challenges and thermal issues with and extending the current VITA standards with some novel approaches and advanced cooling techniques to address some of the challenges that we have. So if we think about kind of where we are today, right? And this group is a testimony to the success of VITA, right? I mean, we've got a large group of people in the press. We've got member companies here. It all shows how well that the VITA model really does work. 12 years ago, right? In fact, it was at this January meeting in 2003 that the call to action went out when people saw that VME was kind of reaching the end of its, I won't say the end of its life because it's still strong, but where VME was reaching kind of the end of its ability to continue to work with some of the newer generation of products coming out there with serial switch fabrics, FPGAs with lots of SerDes on them. And now you have, instead of parallel bus connectivity, you have to be able to connect everything with serial fabrics. And so out of that meeting, out of that call to action, this group responded, and the VPX working group was formed. And in 2006, the first VPX VITA 46 specification was released to the public, and products followed shortly after. And at that time, the group decided to settle on the TE-RT multi-gig RT2 connector, right, which is rated at 6.25 gigabaud. Right, it seemed like a reasonable choice. Signals in 2003 were, the first generation of signals were 3 1/8 and lower, so it seemed like we had plenty of headroom. But by the time the spec was released, we were already starting to see Gen 2 speeds certainly on the horizon. And we've shortly gone from 3 1/8 to 5 to 6.25 to 10.3 now. And we're seeing faster speeds on the horizon, right? So we've blown that 6.25 out of the water. So how do you then go and extend that in an open standards body without special connectors, licensing, proprietary solutions, and being able to use that? And can you do it, right? So that's really the challenge that we're faced with today. And if you think about some of the challenges that we have today, right? Can we do this in an open and reliable system? Can we do this over temperature? Can we, how do we then go ahead and extend the system, right? You think about open VPX now today, right? It's a very flexible architecture, right? So you've got channel lengths of 1 inch, right? If you have adjacent slots, or 17 inches, right? And you've got to be able to support all of that in your system today. Be able to support it again from all the way from the Gen 1 type speeds of 3 1/8 all the way into the Gen 3 speeds of 8 to 10 gigabaud today. And so can we do that? And I really do believe we can. If you think about the challenges we face today, one of my colleagues in the VITA community from another company actually made the statement at several VITA meetings ago when we were talking about this, that Gen 3 is going to separate the men from the boys, right? And Darryl made that statement probably over a year ago now, and that's absolutely true. Right? It is going to separate the men from the boys. You think about the challenges we face today, right? And, I came, when I first started as an engineer, signal integrity wasn't really something we needed to talk much about, right? We were dealing with, 100 megahertz signals. It was always there. You always had to make sure you had reliable signals, but, you had plenty of margin. You didn't really have to deal about it. But now, even when we dealt with 3 1/8, we could get by with a lot of the same rules we use today. You just have to be a little bit more careful with them. But as we start getting into 10, it's a whole new paradigm of what we have to deal with in terms of the knowledge that you need to have of all the aspects of signal integrity and what goes into it. And you just think about all the different things of the different PWB materials and how PWB materials affect loss at these higher speeds, and what PWB materials are appropriate. And even beyond that, things like how the PWB is actually physically made. So things like the weave, how the actual fibers are woven on the PWB affects the skew and propagation delay of differential signals. So you got to deal with that. You got to deal with via technology, right, and how vias are constructed, and you know, whether or not you're using buried vias, blind vias, micro vias, whether you're going to be doing a back drilling of your vias. All of these things are incredibly important as you get to these higher speeds. And even things as arcane as like capacitor construction, right? Because how a capacitor, a ceramic capacitor is made, right, affects the inductance of your signal. And if you do it wrong, you introduce loop inductance and you start ending up with these issues that affect signal integrity, right? And so, you know, to get back to that statement about separating the men from the boys, you think about that, and that's really, like I said, it's a paradigm shift. We really need to understand how all of these things affect signal propagation and signal integrity at these higher speeds. And then, we have to get dogmatic about then developing a comprehensive set of design rules and really adhering to them at the PWB side, right? And that's the module side and the backplane side, right? Because without that, if you kind of relax yourself even a little bit, you're going to find out, you're going to look like that eye diagram, right? It's going to be really closed, and you're going to have no margin or negative margin at these higher speeds, and then, you're going to have products that aren't reliable at these high speeds. The good news is that with proper design techniques, you can achieve open signals, open eye diagrams, and you can get to these Gen 3 types of speeds with adequate margin today, right? And it really is challenging. It takes a lot of time, a lot of effort, a lot of investment to make sure you've got these rules. You've got to do all the upfront analysis work, and then you've got to design something, and then you got to prove that what you've designed actually works with how you analyze things, and it's a big investment, and it's challenging, but certainly it is achievable. And these signals were done with a standard TE multi-gig RT2 connector, nothing special about it. And you can, with these types of proper design rules, you can get to 10.3 and beyond type of signaling rates. Right, you can see even today that many of our companies have introduced in the current draft of the VITA-65 spec Gen 3 rates. So you can see that companies are certainly working on this. Right, Curtiss-Wright has introduced some of these data rates, but so have other companies. Right, there are products that are out there today. Right, we have single board computers, FPGA cards, DSP cards, switches, backplanes that can all operate at these types of speeds. So we know that the community is out there developing and actually has tested and proven, and there are products in customers' hands working today at these types of data rates. So where do we go from here, right? So what's the next step? There's obviously a lot more work that needs to be done. Companies are just starting to get out with their products today. There's certainly more testing that needs to be done. I would say interoperability testing that needs to be done. Most companies, I would say probably all of us have done testing with our own products, but there's work still to be done from that aspect. There's also work in VITA-68, which is a companion spec. They call it the channel compliance spec. They kind of languished for a little while, but now has kind of kicked back in gear. And what that does is define kind of the budgets of your signals throughout from one end to the other end, module to module through the backplane. And that by itself won't guarantee the interoperability, that your products work at Gen 3 type speeds, but it does provide a baseline that companies then can then build upon, and provides kind of a framework in that. So I think that with these proper design techniques, with the work that we're doing, that other companies are doing, we can really achieve this type of reliable operation at 10.3 and above. And I think there is room to grow above 10.3 while maintaining the current VITA VPX modules we have or connectors we have today. And so I do think that things are promising and we can get there. How long, how much further we'll extend it, I think that's still to be determined. At some point, VPX will certainly end, and we'll have to go on to the next thing. But I think we've managed to certainly give it more life to 10.3, and I guess again a little bit further on. And with that, I'm going to hand it over to Ivan.
That's okay, Jerry. I'll fly by the seat of my pants. Yeah. All right. Thanks, Steve. So Steve just talked about some very high-performance systems. These are being used to solve some pretty intense compute problems that our customers are throwing at us. What's powering these high-performance systems? It's basically, high-density, high-power processors, such as some of the Intel ones we've been talking about. Cooling those processors is becoming a huge issue, and it's really affecting product integrity if you don't do cooling properly. Another question that arises is, how can you do this cooling in the truly open and interoperable atmosphere that we know and love within VITA? So those are some of the questions and answers I hope to get through in this presentation. Now, cooling is not the only issue. It's not the only thermal problem that arises with these high-performance systems. The systems that we're going into deployed environments are extended temperature operating environments and also very long lives. And those cause a number of other problems, reliability challenges in addition to cooling. And if I can be specific for a moment, three of them that come to mind, one of which I'm showing here. This one here is basically a positive feedback loop on a phenomenon known as electromigration that's caused by higher temperatures. We've also got things like cold startup conditions that affect commercial devices such as Intel processors, which aren't necessarily rated for -40 to +80 type of environments that we're selling into. And then last but not least, my personal geeky favorite is thermal cycling reliability, but I won't bore you with that details on those. Now, VITA is helping to solve a lot of these problems through things like the VITA 51 series of reliability standards, which have been ANSI approved and out there for a while. And also the VITA 47 environmental standard. And I also mentioned yesterday that we'll be starting up a lead-free working group that'll be along the same vein. But let's get back to cooling though. So the traditional cooling approaches of air flow over modules and conduction-cooled modules are running out of headroom. They've actually run out of headroom. So in order to get that headroom back, what can we do? There are, are a number of approaches that have been proposed within VITA and elsewhere, but we really need to start looking at liquid as well. And there are two main options when you start looking at new cooling configurations. One is you can basically introduce new cooling module standards within VITA. Or another approach is, you can go and look at the chassis cooling approaches. And within VITA, the cooling module standards, new approaches have been introduced already through things like VITA 48.5, which is the air flow through module standard, and VITA 48.7, which is an air flow by module standard. LFT has also been looked at. There's been a number VITA 48 dot spec that was kicked off a number of years ago. It kind of went into hibernation for a while, but it's being rejuvenated. And that we've actually done some work with LFT in the past with Parker Hannifin back in 2007. We proved that you could cool over 650 watts on a 6U module with a 55° C inlet, which is definitely not chilled liquid. So that's a kind of a paradigm shift. Now, one of the issues that arises with if you don't cool properly, if you've got inadequate thermal management, is something called processor throttling. And what that is when you've got some processors, such as Intel, feature these automatic built-in throttling capabilities that discreetly step back the operating frequency in order to maintain a preset and predetermined and measured die temperature, which is great. If you want to maintain that die temperature, it's not so good if you want to maintain maximum performance. So some of the deployed systems, that we sell into are critical A&D systems that demand maximum processing performance in real time. Throttling is not a very good solution. However, it achieves the desired result, which is to keep that operating temperature below typically about 100 degrees Celsius at the die. Now here's one case where processor throttling is actually not a bad thing. If you've got inadequate thermal management, or you've got a device where the power estimate is more than what you thought about in your thermal design, the processor can achieve thermal runaway. That's definitely something you don't want, so processor throttling is good from that perspective as well. Now again, getting back to these high performance systems that we've been talking about, why is cooling such an important issue? There are two main issues with the high performance processors, one of which is the power dissipation that everybody kind of knows, 50 watts, 60 watts, 70 watts, 80 watts. Those are the kind of temperatures or powers that we're looking at these days with the really high performance processors. There's another issue that needs to be looked at, and that's the power density. And in some cases, that can be a much bigger problem than the overall power dissipation of the processor itself. So you really need to address both of those issues in tandem. And at some point, I talked about liquid flow-through cooling earlier. We really need to get to liquid to kind of gain this cooling headroom back. Air is not a bad coolant, but you basically need a hurricane these days to cool some of these high-power processors. If we bring in liquid, you can get back to a gentle flowing stream, and we should be okay. However, it's going to require a continued generation of new standards within VITA. But before we get to LFT, before we actually have to bring in liquid onto the module, we should take another look at what we've done, what we have available to us at this point. And the good news is that previously unobtainable levels of power can be cooled with the focus on the chassis with air and liquid. And we're planning on working on that in 2015 to see how far we can take existing conduction-cooled modules or slightly modified conduction-cooled modules. And with that, I've come to the end of our presentation, and thank you.